Good evening everyone. Myself Sana Sheikh and today I am going to take your week 9 assignment questions. I am a TA of the course NPTEL course named Symmetry, Stereochemistry and Application, and the course instructor is Professor Anshuman Roy Chaudhary from ISR Mohali. So on every Monday from 7 to 9 we are going to discuss the previous year assignment question of this course, that is Symmetry, Stereochemistry and Application. So this is a week 9 live session. So in today's lecture we are going to discuss the previous year week 9 assignment questions. So let's start today's session. So this is a question number 1 of this assignment, where the question is predict the products of the following reaction and indicate whether it is an example of stereoselectivity or stereospecificity. So from the question, I hope all of you are understood that today we are going to discuss the stereoselectivity and stereospecificity of the products formed during the reaction. So this is the first example of the reaction. Here we can see that this is a substituted cyclohexanone. So here the reaction is taking place with lithium aluminum hydride. So which product we will get in this case? So I will write here. So first we have to draw in chair conformation, then it will be easy to understand which will be our major product, or it will be stereospecific or stereoselective. So first we are drawing it in chair conformation. Then at equatorial position I am putting third butyl group, because third butyl group is a bulky group, so it will be more more stable at equatorial position. That's why I am putting it on equatorial position. Now here we have H. These three groups are methyl groups. So please understand this one. These are methyl groups. CH3. All these three are methyl groups. And here we have tertiary carbon atom. That's why it is a tertiary butyl group. Okay. Now we have here, because tertiary butyl group is present at para position, that's why we have drawn here, and here we have oxygen carbonyl group, double bond oxygen. Okay, now when we will treat this substrate with LaH, what we will get, either attack can be done from this side or from this side. Hydride can be attacked from axial position or equatorial position. So which one will be a major product, we have to find out here. So in case of the axial position, if it will attack from the axial side, we will get the product OH H. And the second possibility is that it will attack from bottom side or equatorial position. So in this case, we will get two products, but this one is the major product. Hydride will always attack from the axial position. So this will be our major product, and this will be our minor product. So you can see here we are getting two products, major and minor. equatorial position, because OH has equatorial position is more stable compared to a hydroxy group on axial position, because here a 1,3 diaxial interaction will take place with a hydroxy group. So that's why at axial position hydroxy group is least stable, but at equatorial position it is more stable. Product is more stable. That's why we are getting this one as a major product and this one as a minor product. Huh? हाँ, बट मैंने तो ब्लू होगा. हाँ, सिनेमा ट्यूब में नेम लिखा हुआ. हाँ, yeah. So that's why this one is a major product and this one is a minor product. So because we have to find out in this case stereoselectivity and stereospecificity. So because we are getting major and minor product and not specifically one product, that's why this reaction is comes under stereoselectivity reaction. This reaction is stereoselective because selectively we are getting this one as a major one but not stereospecific, because in stereospecific we are getting specifically only one product. Here we are getting two products, major minor. That's why this reaction is stereoselective. Okay, I hope all of you understood this question. So we can move to the next question. Yeah. So here in this question, again we have to find out the stereoselectivity and stereospecificity. So here we have dibromobutane compound. So because it's a dibromobutane and we have to do the halogenation reaction. So I will prefer to write this substrate in a Fischer projection form. Then it will be easy to do the reaction and explain easily. It will be able to, we are able to draw it in Fischer form. So I am writing here in Fischer form. We have discussed these things stereochemistry in previous lectures. So those who don't know how to convert this molecule in a Fischer projection, please go and watch previous lectures. CH3 and CH3. Okay. Now we have to assign here bromide group. So as you can see here, this is a downside. If we will rotate this molecule, we will see that because in Fischer projection, this CH3 is backside on same side, but here they are in opposite side. So if we will rotate the molecule by 180, we will see that the bromide group will come same side. Both the bromide group are on same side. Here. Okay. Yeah. So this is the molecule we have here for halogenation reaction. So this is a meso compound. As you can see, if we will pass plane through here, we will get the superimposable mirror images of each other. That means it is a meso compound. It is a meso compound. Now we will do the reaction, dehalogenation reaction. That means minus Br2. Dehalogenation reaction minus Br2. When we are doing this reaction, that time elimination will take place here. So when elimination will take place, so we will get E-butene. E-butene. Why E-butene? Because anti-elimination will take place. When anti-elimination will take place, you will observe that these two bromide are on same side if it is cis. So if you will rotate this way, like this way, so this bromide and this bromide are anti to each other. So they will eliminate and a e-butene. We can say e-butene because they are on same side in Fischer projection. That's why e-butene. Specifically, one product only. There is no other possibility of the Z-butene. That's why this is a stereospecific reaction. So either you can write directly this way also. Sorry. Yeah. This is also the product only. E-alkene. E-alkene. E2-butene. Yeah. So because we are getting 100% one product, or we can say specifically one product, that's why this reaction is comes under stereospecific condition. Because of substrate specificity. Stereospecific. Right here. Okay, so I hope this substrate is also clear to you. This question is stereospecific related question. So I hope all of you are clear here. So we will move to the next question. Yeah. Which compound is it? It is cyclohexane. Yeah. Here you can see that we have halogen and methyl group adjacent to each other, and this is the cyclohexane. So or ortho substituted, iodo substituted, toluene we can say. So here what we have to do, we have to find out the product of the reaction and their stereospecificity or selectivity. Stereoselectivity. So when we have this type of product, we have to write in chair conformation. Always we have to write in chair conformation. After writing in chair conformation, we can see at which position they are present. So because they are cis, you can see here both the substituent are on wedge position, that is above the plane. So that's why above geometry will be preferred here, or down below either we can draw. So here I am drawing like this axial equatorial. So this is a cis isomer of this compound. So because here we have given cis only, that's why I am drawing this way. Now if we will treat this one with KOH and ethanol, KOH and ethanol, what will happen? Here we have hydride, proton. Here also we have proton. So elimination will take place here. So this proton will be eliminated, abstracted by a base KOH, and this halogen will, because it's a good living group, it will be eliminated through here. So here basically we will observe the HI elimination. HI elimination. So after elimination we will get the product, that is cyclohexene. Right? This one. But there is one more possibility is there. What is that possibility? Hydride can go through proton can go through from this carbon also, because this carbon also have CH2. So if proton will abstracted from this one, because always the trans elimination is anti elimination is taking place. So here you can see I and proton both are anti to each other. That's why it's eliminated. So because this carbon also have both the anti and cis proton, so it can also undergo elimination. So we will get the one more product, which is like this one, correct? Because here also the possibility of elimination is there. Okay, so this will give two type of products, not one only. So because we are getting here two products, so that's why the reaction is become stereoselective, not the stereospecific. So this reaction is example of stereospecific, sorry, stereoselective. Sorry for the mistake. Stereoselective, correct? This is the example of stereoselective reaction. If we will take the other way, like if I will draw here, this is our wedge position where iodine is present, I group, and this is back of the plane where we have methyl group. Okay. Now we have to write this one in chair conformation. Okay. Now we have to draw the iodine here, because they are trans to each other. So methyl group will go axial only, because they are trans to each other, anti to each other. Okay. Now here we have proton Here also we have proton. So when the elimination will takes place, base will abstract the proton from this site only, this carbon only. Why? Why this carbon only? You can see here, here this iodine have anti group, methyl group. So here there is no proton is present anti to the iodine group. So because anti elimination is taking place is favorable, that's why here, because this carbon have both the anti and cis proton to the iodine, that's why elimination will take place from here. Here you can see only sin same side proton is present. From same side it cannot be abstracted, because anti-elimination is favorable. That's why we will get here, because here we have both the protons, anti as well as sin. Okay, so that's why we will get only one product, that is this one. So this is the specifically one product. So that's why this type of reaction will become the stereospecific reaction, because specifically we are getting only one product. So here I hope from these two examples you have understood which one is stereospecific and which one is stereoselective reaction. So the second one is stereospecific, because only one product specifically we are getting here. Stereospecific. So I hope this one is also clear to you. So we will move to the next question. Yeah. Again, in this question, we have here cyclohexene, ethyl substituted cyclohexene. So here it will be, when it will be treated with bromine, what will be the product? So I am going to write here we have this one. When bromine will attack on this double bond, we will get a 3-member ring with bromine, either above the plane or below the plane, depending on the ethyl group configuration, ethyl group stereochemistry. So if ethyl is present on front side, suppose present on front side, on above the plane, then this bromide will form 3-member ring from back side. Correct? Okay. Now Br manus will attack from which side? We have Br manus here, right? Br manus is our nucleophile which will attack. So it can attack either from this side or from this side, but which will be favorable? Which will be favorable? So because it's always, nucleophile will always prefer attacking from a lower substitution side. So here you can see that here substitution is high because ethyl group is present. Here ethyl group is not present. So it's a less hindered side, less substituted side. So the product will form here will be from this side, major product. Bromide. And here from, and always remember that if it is present on back side, this remembering, then attack will be preferred from opposite side. So that's why bromide will attack from front side, from above the plane, and from lower substitution side. So this will be the major product, and the other product possibility is there, which is this one. No, sorry for the confusion. This bromide cannot attack from this side because front side is already occupied. It is already occupied. So only one possibility is there in this case. It can attack only from the other side. It can attack only from other side. That's why we will get specifically one product. Specifically one product. If ethyl group was not there, if it will be absent, then we will get two different products. So I will discuss that case also. But this reaction is stereospecific reaction because we are getting specifically one product, because this side is blocked. From here bromide cannot attack because from downside this is 3-member ring is there, and on above the plane ethyl group is present. So both the faces are occupied. That's why this reaction is stereospecific reaction. Okay, and the other possibility is also there. Other example I will give here to make clear. Suppose we have another example where we have only protons. There is no ethyl group. H, and this bromide will attack here below the plane. Below the plane. So when the Br manage attack, when Br manage will attack here, it has two possibilities. Either it can attack from this side or it can attack from this side. Why? Because here we have proton. Here we have a vacant side, but here we don't have. Here because of the ethyl group, here steric hindrance was there, so possibility was not there to attack from that side. That's why in this case we got only one stereospecific product, but here we have a possibility of both the attacks. So here we will get two types of product. Sorry. If it will attack from this side, front side, Br will come on front position, front side, Br. Correct? And the other possibility is there. Br and Br. Correct? So basically in this case we are getting trans product. Both the products are trans, but because both are not same, they are enantiomers. That's why this is a stereoselective reaction, because specifically we are not getting single product, but we are getting two products. That's why this reaction is comes under stereoselective reaction. So with this example, I hope all of you are clear. Stereoselective reaction. For detailed answer and for concept, please go through the YouTube videos available on Symmetry, stereochemistry and its application channel on YouTube. Please find out the same on YouTube for better understanding. Then this is the next question. So here we have carbonyl carbon which is treated with LAH reaction in dry THF and followed by hydrolysis. What will be the product for this one reaction? Anyone can guess this one? Which rule will be applicable for this type of reaction, or which model? This is a Falcon and model based question. So, what is Falcon and model? So, Falcon and model is based on a computational approach. They propose the carbonyl addition reaction that would preferred for the lowest energy transition state, where the large group is perpendicular to the carbonyl bond, and the reacting nucleophile preferentially approach the carbonyl group from the side which is remote to Cl group, that means from small group side, maintaining obtuse angle with carbonyl bond. So I will write the structure here. First of all, you should understand what is Falconine model. So I am drawing Newman projection for Falconine model. This is a general example only, not for this question. I will draw this for this question separately. Oxygen, R group, NER group. Now we have three substituent on adjacent carbon atom. So large group will always come perpendicular to carbonyl group. This is carbonyl group and this one is perpendicular to carbonyl group. So always remember it should come perpendicular to carbonyl group. If it will become perpendicular to carbonyl group, then medium and small group will come this way. Medium and small. One more possibility is there, because according to rule only large group should be perpendicular to carbonyl group, but medium and small group can be interchanged here. Suppose is our carbonyl group. Here we have R group, L, which is perpendicular to carbonyl group. Now here we have M and S. So there are two possibilities, two possible conformers. So first one will be preferred one, because R group is lie between the this R group is lie between the small and large group. So the repulsion steric hindrance will be less in this case. That's why this is the more preferable one. This first one is more preferable one compared to the second one. Okay. So I hope so this concept is clear. Now we will discuss our question. This is our carbon Falconen model I am going to draw here. So this is our carbonyl group. I am looking from this side. So this carbonyl group is present on front carbon. That's why I am writing this way. Oxygen. Then ethyl group. Correct? This ethyl group. Now while taking the back carbon, this group have one methyl group, one hydrogen and one long chain ring. So this long chain I will consider as a large group. So that's why I will draw it on perpendicular position. So on perpendicular position I am going to write here large group, that is CH2 CH2 CH phenyl methyl group. So that's why I will write only L, directly L. I am not going to write the whole group. You can write whole group here, but here I am writing only L because it's a large group. Correct? Now we have to write here small and medium group. So you can see here methyl and hydrogen are there. So hydrogen is smaller one. Correct? So it will come here and methyl will be here. Now attack will take place from this side. Lithium aluminum hydride reaction it is, and because here we don't have any hydroxy group, so that's why there is no hydrogen bonding will be present in this molecule. So directly Falconen model will be followed, and hydride will attack from either this side or from either it will attack from this side here, or it will attack from this side. So as you can see that because this attack will be between ethyl and large group, so it will be less favorable. But here you can see small and ethyl group, small and R group have less hindrance, so attack can be preferred from this side. So when hydride attack will take place from here, hydride attack will take place, then what we will get? We have methyl. I will draw first back carbon. Methyl, large group. it will remain here, here, this way. Here we have OH, ethyl, and hydride. So attack will always be preferred from less hindered side. So because hydride attack is taking place from this side, this OH group will go here and this side, and hydride will come this side. The other possibility is, of product is there. It can attack from this large group side. So when it will attack from large group side, we will get the product here. I will write between the ethyl and large group. So here you can see attack is taking place from between small and R group side. But here, if it will take place between R and L, between R and L group, so it will be hindrance side product, but it will give this as a product. I will write here. So this ethyl will go this side because attack is taking place from this way. So this will move this side. So here we have hydride, OH, and here we have large group hydride and medium. Okay, okay. So here we have this one as a major product. This one as a major product because attack from less hindered side will be more preferable compared to the more hindered side. So this is our minor product. So because we are getting here major and minor both the products, but not getting a single product specifically. So that's why this reaction comes under the example of stereoselectivity reaction. This is a stereoselective reaction. Stereoselective reaction. This is an example of stereoselective reaction. So we have done here 5 examples. I will revise all those examples one by one. So I hope all of you are clear with these examples. So let's do it. And if you have any difficulty, doubt regarding these questions, you can discuss with me on YouTube channel. In today's session, we have discussed the stereospecificity and stereoselectivity of the product. So in this case, in first reaction, we have observed that we have drawn this cyclohexane in a chair conformation, and we have observed that there are two possibilities of hydride attack. Nucleophile will attack from either axial position or from equatorial position. So if it will attack from the axial position, we will get this one as a product. But while hydride will attack from the backside or a equatorial position, we will get this as a product. As I told you, because hydroxy group is more stable at equatorial position because of lone pair uh, and the bulkiness of this hydroxy group, this equatorial position is more stable. That's why we are getting this one as a major product. While in the other case, here we are getting OH as a hydroxy group at axial position, where we observe the 1,3 diaxial interaction and lone pair interaction also. That's why this is our minor product. So this one is the major product and this one is the minor product. And that's why, because we are getting here two products, not the single stereospecific product, that's why this reaction comes under stereoselective reaction. Because specifically we are not getting a one product, we are getting a mixture of two products, but one is major and other is minor. So that's why this reaction comes under stereoselective reaction. Okay, clear? Now, this is the second question we have done today. So, in this case, we have to again predict the product. So, for product prediction, we have written this substrate in a Fisher projection form. So, in a Fisher projection form, we have observed that both the bromine atom are on same side. So, because they are a meso compound, here you can see pass the plane. You can see here this is a meso compound. Mirror image of each other, mirror plane you will observe here, and because of the meso compound, so always anti-elimination is favorable, and they both are same side. So it will rotate by 180 to give this one only. Rotation, sorry, yeah, rotation by 180 degree on one carbon. We can give numbering 1, 2, 3, 4. So we can see here 2, 3, carbon number 2, 3 undergo rotation to give this compound, and this will rotate to give this one. So after rotation we can do the anti-elimination, and anti-elimination will give here E2-butene product. E2-butene, because they will become trans to each other, both the bromine atom, and it will undergo elimination to give the E2-butene. And because here we are getting only single product, there is no possibility for the Z conformation formation. Z isomer will not form in this case. That's why this reaction comes under stereospecific reaction, because specifically we are getting only one product. Only one product here we are getting. No minor major product will form in this case. Only one major product will form, which is called as stereospecific reaction. So this is this reaction is an example of stereospecificity. Now, next we have discussed the question which have the halogen group as well as uh, alkyl group present on the ring, cyclohexane ring. So here we have written in chair conformation for better understanding, and we have observed that iodine and methyl both groups are on same side, that is syn to each other. Syn elimination can syn to each other, that is cis. That's why we have drawn here axial and equatorial position. Both are above the plane. Both are above the plane, from that means both are same side. So here a base will abstract the proton from either this carbon or from this carbon. So where is the major possibility? So here you can see that in this case this proton is present anti to this iodine, anti, and this proton is anti to this iodine. Here it's present, right? So because anti-elimination is preferable, so that's why I will draw here first proton. Here also we have proton, correct? Okay. So because anti-elimination will takes place from here, so we will get this as a product. This as a product. Okay. While there is other possibility also, it here, because this carbon, this adjacent carbon also have cis and trans both the protons available. So here also, because trans proton is available, so it can undergo elimination, and after elimination it will give this product, the second product we can say. I will write here first, second, 1, 2. So because here we are getting two different products, from the same substrate and same reaction. That's why this, this reaction is not stereospecific, because we are getting two products, not single product with specificity. That's why this reaction comes under stereoselective reaction, and this is the example of stereoselective reaction. Why the other case we have discussed here, if this iodine and methyl group are anti to each other, if they will be anti or trans to each other, here we have cis example. But if what will happen if they are trans to each other? So we have drawn here chair conformation, and we have observed that iodine and methyl group both are at axial position because they are trans to each other, right? When the elimination will take place, abstraction of proton will take place. So here, if this proton will be abstracted, then because iodine is not anti to this proton, so it is not the favorable one. So because this iodine will eliminate this and anti to this carbon, the proton which is anti to this iodine will be abstracted, and we will get only single product, because only at this carbon atom we have anti proton present. Here we have the cis proton, because hydrogen and iodine both are on same side, so they can't undergo elimination reaction. That's why this carbon adjacent carbon atom will lose the proton to give the desired product. So this will be the only product in this case because of the stereospecificity, because here there is no possibility of abstraction of proton from the same side. That's why we are getting only this product. So because the only one product formation is taking place in this reaction is the example of stereospecificity. Okay, and this reaction is comes under stereospecific reaction. This is also clear to you? Okay, now let's discuss this one. So here we have discussed the halogenation of this product. So when the halogenation, this product, substrate is undergo halogenation reaction. So first the three member cyclic ring formation will take place with Br plus. So when this intermediate will form, then Br minus, which is nucleophile, will attack either from this side or this side. So you can see that here this upside ethyl group side is blocked, because front side ethyl group is present and back side this three member ring is present. So there is no possibility for attack of this side. But in other hand, you can see that here we have less hindered group. Only front side is vacant to attack. So this nucleophile will attack from front side to give this as a product. So because here we are getting only single product, there is no other possibility for the second product. That's why this reaction comes under stereospecific reaction. This reaction is an example of stereospecific reaction, and we can discuss this same reaction with the other example also. If we don't have this ethyl group as a substituent on this carbon, then what will happen? So then after forming this three member cyclic ring, there are two possibility for nucleophilic attack. Either it can attack from this side, or upside we can say, or it can attack from this downside at other carbon atom. So if we attack from this side, we will get this product, because front side is vacant, because this Br tricyclic ring is back side. So Br will attack from front side. So we will get this as a product. And the second, according to the second possibility, we will get this one as a major product, because ring opening will take place from this side. So because here we will observe two product formation. There are two product formation is taking place in this case. That's why this reaction is comes under stereoselective reaction. It's an example of stereoselective reaction. I hope all of you are clear here till here. Now we will discuss the last question, which is based on our Falconen model. So as I discussed with you, what is Falconen model? So Falconen model is based on a computational approach. All of you know that, and they propose that the carbonyl addition reaction would be preferred for the lowest energy transition state, where the large group is perpendicular to the carbonyl bond, and the reacting nucleophile preferentially approach the carbonyl group from the side which is large group is maintaining obtuse angle with carbonyl group. Obtuse angle with carbonyl group. So here I have already told you because we according to Falkenhayn model we have drawn that large group is perpendicular to the carbonyl group, and this is this one I am considering as a large group, this whole group, right? Now because small group is hydrogen here, proton, so I am drawing here, writing here proton here, because less repulsion will take place between ethyl and proton. This is the most stable conformation according to the Falkenhayn model, and methyl group will come here, medium group. Now attack of hydride can happen through this side also and from this side also, either from this side or from this side. So when it will attack from this side, that means it will attack from between the medium and small and R group, small group and R group, and the other possibility of attack is there between the R group and large group. So because large group is bulky, so this is the more hindrance side, and it will give a minor product because it is a less favorable condition, while the other side attack from the smaller group side will be a major product because it will minimize the hindrance between the R group and this substituent present on the adjacent carbon atom. That's why we will get this one as a major product. So after getting this major minor product, now we can say that because in this reaction we are getting the two different products, major and minor, not the specifically one product. That's why this reaction is comes under stereoselective reaction. This reaction is an example of stereoselective reaction. Understood? I hope all of you are understood the difference between the stereoselective and stereospecificity reactions. When the only one product we are getting, that time the reaction is stereospecific. But when we are getting more than one product, that time the reaction is stereoselective. Okay. Here you can see that question number 1. This one is a stereoselective reaction. Then the second one is stereospecific reaction because only one product is there. Then the third one we are getting the stereoselective reaction because we are getting two types of products. Then in the fourth question we are getting the stereospecific product, only one product formation is taking place, right? Then in last case, this is the example of stereoselective reaction. Okay. I hope all of you are clear till here. If any doubt, any difficulty, any question regarding these things are there, you can ask me in YouTube channel in comment section. So I would like to solve your problems. Thank you so much for your kind attention.